Today we are going to learn about the magical world of divisibility rules, those neat little shortcuts that save us from the absolute chore of long division. Ever looked at a massive number and instantly known whether it could be split perfectly into smaller groups without actually doing the math? That is divisibility in action. And just like parity, it has a set of ironclad rules it always follows. Even numbers are the neat, predictable folks of the number world. They always follow the golden rule. They can be divided perfectly by 2 without leaving a remainder. But what about dividing by 3, 4, or 9? Let us lay out all the signs, the trusty workhorses of our mathematical society. For 2, the number must end in 0, 2, 4, 6, or 8. For 3, you add up all the digits. If that sum is divisible by 3, the whole massive number is 2. For 4, look at the last 2 digits. If they form a number divisible by 4, you are golden. For 5, the number just has to end in a 5 or a 0. For 6, we get to combine our powers. Since 6 is built by multiplying 2 and 3 together, any number that wants to join the 6 club has to perfectly satisfy the rules for both of those foundational building blocks. It is a strict two-step verification process. First, you just check if the number is even by glancing at that very last digit. If it is odd, it is instantly rejected, no questions asked. But if it passes that first test, you then move on to adding up all the individual digits to see if their total is a multiple of 3. It absolutely must pass both tests without fail to be cleanly divisible by 6. For 8, look at the last 3 digits. If they are divisible by 8, the whole number is. For 9, it is exactly like the rule for 3. If the sum of all the digits is divisible by 9, you have a winner. And for 10, the neatest of them all, the number simply must end in 0. But wait, you might be asking, what about 7 and 11? Oh, those are the true misfits, the rule breakers of the division world. I am going to keep their bizarre boss-level secrets locked away, and I will only reveal them at the very end of this movie. Stick around. To truly prove these rules, we need to look at the anatomy of any whole number, no matter how ridiculously huge it is. Because we operate in a base 10 mathematical society, every single integer is just a combination of digits multiplied by powers of 10. Let us say we have a massive number. Mathematically, the absolute ironclad definition of our number is its first digit from the right, plus 10 times its second digit, plus 100 times its third digit, and so on. Let us break down the proofs and see exactly which digits actually work. Another truth we need to understand is the divisibility rule of sum of numbers. Have you ever looked at a massive math problem, a huge sum of numbers, and wondered if the whole thing is divisible by a specific number? There is a beautiful, simple rule for this that saves us a ton of work. Let's say you have 2 integers, a and b, and you want to know if a divisor, let's call it k, divides their sum. Here's the truth of it. If you already know that your number k divides it perfectly, then the entire problem boils down to just checking b. If k divides b, it divides the whole sum. If it doesn't, it doesn't. To prove this rigorously, we have to show that this is a two-way street. We need to prove the forward direction, and then we need to prove it in reverse. First, let's assume k divides a, and it also divides b. By definition, this means a is just some multiple of k. Let's call it k times m. b is also a multiple of k. We'll call that k times n. Now, let's add them together. But plus b is exactly the same as k times m plus k times n. If we factor out that common k, we get k multiplied by the quantity m plus n. Since adding 2 whole numbers always gives you another whole number, we've just shown that the total sum is a perfect multiple of k. Now let's flip it. Let's assume we know k divides a, and we also know it divides the total sum, a plus b. Does it have to divide b? Well, if the total sum is a perfect multiple of k, let's call that total k times p. And we already know a is k times m. To isolate b, we just subtract a from the total sum. So b is equal to k times p minus k times m. Factor out the k again, and you get k multiplied by the quantity p minus m. Just like with addition, subtracting one whole number from another leaves you with a whole number. Therefore, b must also be a perfect multiple of k. The proof is complete. Why is this so powerful? Because it lets us strip away the noise. When you are testing a massive sum for divisibility, you can immediately cross out any chunks you already know or multiples of your divisor. They effectively become irrelevant. The divisibility of the entire system rests entirely on whatever unknown pieces are left over. It's a perfect example of how math lets us break massive computational problems down into bite-sized pieces. Now let's see why do the rules for 2, 5, and 10 only care about the very last digit. Look at our numbers anatomy. Every single place value except for the last one is a multiple of 10. We can factor out a 10 from everything except that final unit digit. This means our massive number simplifies elegantly to 10 times some giant chunk of integers, plus the last digit. That entire first chunk always vanishes perfectly without a remainder when we divide it by 2, 5, and 10. Applying the divisibility rule of sums, the divisibility of the entire number rests entirely on that single, solitary digit dangling at the end. For 2, the winning digits are exactly 0, 2, 4, 6, and 8. Sorry to digits 1, 3, 5, 7, and 9, but you are officially not invited to the division party of 2. For 5, the winning digits are exclusively 0 and 5. Any other ending, whether it is 1, 2, 3, 4, 6, 7, 8, or 9, instantly rejects the number and makes it completely indivisible by 5. For 10, the absolute only winning digit is a perfect 0. Anything else makes the number indivisible. But look at this from another mathematical perspective. Since 10 is exactly 2 times 5 that do not share common factors, any number divisible by 10 must also perfectly pass the tests for both 2 and 5. And the only digit that proudly sits in both of those winning circles is 0. The rules for 4 and 8 are just leveled up, supercharged versions of the rule for 2, 5, and 10. Let us look at the rule for 4 first. We know that 10 is not a clean multiple of 4. If you try to divide 10 by 4, you are left with an awkward remainder. But 100 absolutely is a perfect multiple. Just think of how 4 quarters make a dollar. Or mathematically, 4 times 25 perfectly equals 100. Because of this fact, any multiple of 100, whether it is 200, 700, or 53,000, will always divide cleanly by 4. So, we adjust our mental anatomy of the number by factoring out 100 from every single digit, starting from the hundreds place and moving left. That huge chunk of the number, let's call it part A, no matter how ridiculously massive it is mathematically guaranteed to be divisible by 4 without breaking a sweat. It completely vanishes from our worry list. What is left over? Just the tens and units places combined. Let's call this part B. Applying the divisibility rule of sums, since our divisor 4 perfectly divides the massive chunk, part A, the divisibility of the entire number rests solely on part B. Therefore, a number is divisible by 4 if and only if its last 2 digits combined form a number divisible by 4. To see exactly how this vanishes the worry list, let's break down a couple of numbers using this anatomy. Take the number 5,732. We can break this down into 5,700 for part A plus 32 for part B. 5,700 is a multiple of 100, so it is guaranteed to be divisible by 4. We can completely ignore it. Now for part B, we only look at the last 2 digits, 32. Since 32 divided by 4 is exactly 8 with no remainder, the rule of sums dictates that the entire number works. 5,732 is cleanly divisible by 4. Now let's look at a much larger number, like 914,018. We break this down into 914,000 for part A, plus 18 for part B. That massive first chunk is a multiple of 100, guaranteed to be divisible by 4, so we ignore it. We look at the last 2 digits, 18. If we try to divide 18 by 4, we get 4 with a remainder of 2. Because part B fails, the rule of sums tells us the entire massive number, 914,018, is not divisible by 4. Now, let us take that exact same logic and level it up one more time for the number 8. Just like 10 failed our test for 4, 100 fails the test for 8. If you try to divide 100 by 8, you get 12.5, so it does not divide cleanly. But what happens when we go 1 power of 10 higher? 1,000 absolutely is a perfect multiple of 8. 8 times 125 equals exactly 1,000. Because we know this is true, that same mathematical magic happens again. Any multiple of 1,000, whether it is 5,000, 80,000, or 400 million, is mathematically guaranteed to divide cleanly by 8. We can take our massive number, slice off the thousands place and everything to the left of it, and completely ignore it. Let us call this giant slice part A. All of those higher digits are already perfect multiples of 8, so they completely vanish from our calculation. This means the entire problem of figuring out if a massive, sprawling number is divisible by 8 drops down to just looking at the last 3 digits, which we will call part B. Applying the divisibility rule of sums, since 8 perfectly divides part A, the entire gigantic number is divisible by 8 if, and only if, part B can be divided by 8. It is a brilliant computational shortcut that strips away all the excess data and leaves you with only the 3 digits that actually matter. To see this shortcut in action, let us test the number 74,816. We slice this into 74,000 for part A and 816 for part B. That first 74,000 is a multiple of 1,000, so we know 8 divides it perfectly. We throw it out. Now we just look at part B, 816. 8 goes into 800 100 times and into 16 2 times, giving us exactly 102 with no remainder. Because part B works, the entire number works. Now imagine a ridiculous number, like 5,211,150. We slice off the millions and thousands to make part A, which is 5,211,000. Because it is a multiple of 1,000, it vanishes from our worry list. We are left with part B, the last 3 digits, 150. If we try to divide 150 by 8, we get 18 with a remainder of 6. It does not divide cleanly. Because part B fails, the rule of sums tells us that the entire 5 million something number is not divisible by 8. Why on earth do we sum the digits to test for 3 and 9? This is where the algebra gets beautifully clever. We know intuitively that any power of 10 can be written as a string of 9s plus 1. But let us definitively prove that any power of 10 minus 1 is always a pure multiple of 9. Sometimes, the best way to understand a number is just to look at the pattern. 10 to the first power minus 1 is 9. 10 to the second power minus 1 is 99, which is 9 times 11. 10 to the third power minus 1 is 999, which is 9 times 111. Every time you take a perfect power of 10 and subtract 1, the result's simply a solid string of 9s. Because the number is entirely made of 9s, it is undeniably divisible by 9. If we want a more traditional algebraic proof, we can use the universal formula for factoring the difference of powers. In algebra, any base number raised to a power minus 1 can be factored into that base minus 1, multiplied by a long sequence of descending powers. When we plug our base of 10 into this formula, that very first factor becomes 10 minus 1, which is exactly 9. Since the entire massive expression is now exactly 9 multiplied by some other integer chunk, it is absolutely a multiple of 9. To achieve ultimate mathematical rigor, and prove this for every number to infinity, we use proof by induction, which works exactly like knocking over an endless line of dominoes. We want to establish that for any positive whole number n, the expression 10 to the power of n minus 1 is always a perfect multiple of 9. First, we prove the very first domino falls. 10 to the first power minus 1 is 9. Since 9 is obviously a multiple of 9, our base case is solid. Next, we assume our rule holds perfectly true for some random, unspecified power in the middle of the line. Let's call it k. We are accepting as fact that 10 to the power of k minus 1 is definitively a multiple of 9. Now we must prove that if domino k falls, it mechanically forces the next domino k plus 1 to fall as well. We look at the next power, 10 to the power of k plus 1 minus 1. Here is where the math gets elegant. 10 to the power of k plus 1 is exactly the same thing as 10 multiplied by 10 to the power of k. To connect this back to our assumption, we use a classic algebraic trick. We subtract 10 and then immediately add 10 right back in. This changes how the equation looks without changing its value. It becomes 10 times 10 to the power of k minus 10 plus 10 minus 1. By factoring out a 10 from the first two pieces, we group our terms perfectly. It becomes 10 multiplied by the quantity, 10 to the power of k minus 1, all plus 9. Look at that. Our exact original assumption, 10 to the power of k minus 1, is perfectly isolated in the brackets. Because we already know that bracketed assumption is a multiple of 9, and the extra piece on the end is exactly 9. Both parts of our new equation are perfectly divisible by 9. We have mathematically guaranteed that the next domino will inevitably fall. Now, think about how we build any number in our base 10 system. Let's take a generic number and break it apart into its digits. We will call the ones digit d0. the tens digit D1, the hundreds digit D2, all the way up to our final largest digit, which we will call Dn. Written out, a number is just a massive addition problem. It is D0 plus 10 times D1 plus 100 times D2, going all the way up to 10 to the power of n times Dn. We just proved that mathematically, every single power of 10 can be rewritten as a multiple of 9 plus 1. So let's swap out those powers of 10 in our expanded number. Instead of 10 times D1, we substitute our generalized formula and write the quantity 9 times K1 plus 1 times D1. Instead of 100 times D2, we write the quantity 9 times K2 plus 1 times D2. We do this substitution for every single place value in the entire number, using a new K variable for each power of 10. The number becomes D0 plus the quantity 9 times K1 plus 1 times D1 plus the quantity 9 times K2 plus 1 times D2, all the way up to the highest digit. When we distribute our digits into those parentheses, something beautiful happens. Every single term splits into two distinct parts. One piece securely attached to a multiple of 9, and a second piece which is just the isolated digit itself multiplied by 1. Now, we just rearrange the furniture. We take all the pieces attached to a 9 like 9 times K1 times D1 and 9 times K2 times D2 and group them together on the left side. Because every single one of those terms shares a 9, we can factor that 9 completely out to the front. Let's package that entire massive section into one clean variable. We will call it part A. What is left over sitting on the right side? Just the isolated digits themselves, D0 plus D1 plus D2, all the way up to Dn. Let us call this part B. We have brilliantly transformed our original number. We proved that absolutely any number in the universe can be rewritten as a giant multiple of 9, plus the sum of its digits. Let us tie this directly back to our fundamental rule of sums. We established that if a divisor perfectly fits into the first chunk of an equation, part A, the divisibility of the whole thing comes down entirely to the second chunk, part B. Since part A is literally constructed to be a multiple of 9, we know with absolute certainty that 9 divides it perfectly. Therefore, it is entirely sufficient to just look at part B, the sum of the digits. If 9 can divide that simple sum, we have mathematically proven that 9 divides the entire original number. Let us test the number 5,436. We add the digits together. 5 plus 4 plus 3 plus 6 equals 18. Since 18 is a clean multiple of 9, the original number 5,436 is officially welcomed into the 9 club. Let us try a massive number for 9, like 72,999. 7 plus 2 plus 9 plus 9 plus 9 equals 36. 36 is a perfectly clean multiple of 9, so 72,999 gets a VIP pass. But what about a number that doesn't work? Let us try 8,241. We add the digits together. 8 plus 2 plus 4 plus 1 equals 15. Since 15 is not a multiple of 9, the rule of sums tells us that the entire original number, 8,241, is not divisible by 9. And here is the absolute best part. This exact same structural breakdown gives us the rule for the number 3, completely for free. Since 9 is just 3 times 3, our massive part A is not just a multiple of 9. It is inherently a perfect multiple of 3 as well. If the number 3 can divide the leftover sum of the digits, it mathematically guarantees that 3 divides the entire original number. Let us test the number 426. Since 12 is a clean multiple of 3, we know for an absolute fact that 426 is completely divisible by 3. For a quick check, let us try 111. 1 plus 1 plus 1 equals 3. It passes the test effortlessly. Now what about 6? The proof is beautifully simple. Since 6 can be factored into 2 times 3, any number that wants to join the 6 club has to perfectly satisfy the rules for both of those foundational building blocks. In higher mathematics, this relies on the fundamental theorem of arithmetic and the concept of coprime factors. Because 2 and 3 share no common factors other than 1, any number that is cleanly divisible by both 2 and 3 is mathematically guaranteed to be divisible by their product, which is 6. It is a strict two-step verification process. First, you just check if the number is even by glancing at that very last digit. If it is odd, it is instantly rejected, No questions asked, as it is not divisible by 2. But if it passes that first test, you then move on to adding up all the individual digits to see if their total is a multiple of 3. If it passes both tests without fail, it is officially divisible by 6. Let us test an example for 6 to see this in action. Take the number 432. First, we check if it is even by looking at the last digit, which is a 2. Since 2 is in our winning club for 2, it passes the first test. Next, we add up all its digits. 4 plus 3 plus 2 equals 9. Since 9 is a clean multiple of 3, it passes the second test. Because 432 passes both tests without fail, it is officially divisible by 6. Now for the boss level challenge, the number 7. 7 is notorious in mathematics because its divisibility rules are not immediately obvious. You cannot just look at the last digit, and you cannot just add them all up. But using the exact same logic we have been building on, we do not need to memorize a confusing rule. We can actually construct it ourselves. We just need to find a way to make the massive problem smaller. Here is how we set it up. Take any random number and chop off its very last digit. We will call that final single digit b. We will call the entire remaining front part of the number a. Because our number system is based on tens, we can say our original number is exactly equal to 10 times a plus b. For a quick example, picture the number 84. If we chop off the last digit, a is 8 and b is 4. 10 times 8 plus 4 gets us right back to 84. Now, how do we use this structure to find a chunk that 7 perfectly divides? Let us look at two different ways to break it down. Let's take our equation, 10 times a plus b, and split that 10a into two separate pieces, a 7a and a 3a. Our original number is now written as 7a plus 3a plus b. Look at that very first piece, 7a. It is literally a multiple of 7. Since we know 7 divides it perfectly, we can cross it right out. It completely vanishes from our worry list. Therefore, it is entirely sufficient to just check the leftover piece, 3a plus b. If 7 divides that much smaller chunk, it mathematically guarantees that 7 divides the whole number. Let's test it out. Is 91 divisible by 7? Here, our front part a is 9, and our last digit b is 1. We multiply a by 3, which gives us 27, and add b, which is 1. 27 plus 1 is 28. Since we all know 28 is a perfect multiple of 791, absolutely must be as well. Math is incredibly flexible. And of course, we could use a completely different approach to shrink the problem. What if, instead of breaking 10a apart into smaller addition pieces, we intentionally overshot it? We can rewrite 10a as 14a minus 4a. If we plug that back in, our original number is now structured as 14a minus 4a plus b. Why use 14? Because 14 is a perfect multiple of 7. That entire 14a piece is mathematically guaranteed to be divisible by 7. So once again, we cross it out and completely ignore it. We are left with checking if 7 divides the remainder, negative 4a plus b. Now, since I like to keep things positive, I do not love dealing with a negative sign right at the front of my equation. Fortunately, we can use a simple mathematical truth. If a divisor perfectly divides a number, it also perfectly divides its exact opposite. For example, if 7 divides 21, it perfectly divides negative 21. Because of this rule, we are allowed to simply flip the signs on our leftover chunk. Instead of checking negative 4a plus b, we can check its exact opposite, 4a minus b. Let's test this one. Is 112 divisible by 7? Here, our front chunk a is 11, and our last digit b is 2. We multiply it by 4, which gives us 44, and subtract b, which is 2. 44 minus 2 is 42. Since 42 is perfectly divisible by 7, the number 112 is completely divisible by 7. We just took a complicated, intimidating number and effortlessly smashed it down into basic, bite-sized arithmetic. But can we do better? Here we need to multiple a. Can we use as is? We absolutely can. Let us build the famous rule for 7 from the ground up, using pure intuition. This will show us exactly why we can use that massive front chunk, exactly as it is, without scaling it up. Imagine our giant number. We chop off the last unit digit and call it b. The entire remaining front part is a. Because of how our base 10 system works, our original number is algebraically written as 10a plus b. So let's make a bold move and scale the whole problem up. We multiply the entire thing by 2. 10a becomes 20a, and b becomes 2b. Our new scaled up number is 20a plus 2b. But wait, if we double a number, haven't we completely changed it? How can testing this new doubled number tell us anything truthful about the divisibility original 1 by 7? Here is the secret. It works perfectly because of a massive mathematical catch. The number we are multiplying by 2 and the number we are testing for 7 share absolutely zero common factors. Because they have nothing in common, their relationship creates a perfect two-way street. Going forward is obvious. If 7 perfectly fits into a number like 21, it will obviously fit into double that amount, 42. You just have twice as many 7s. But the reverse is where the true magic happens. If 7 cleanly divides our doubled number, we have a mathematical guarantee that it perfectly divided the original number too. Let us prove exactly why this reverse direction is completely bulletproof. Think of numbers like molecules made up of prime number atoms. Every single number has a unique recipe of prime atoms that build it. If 7 divides a number perfectly, it means 7 is literally one of the fundamental atoms inside of it. Imagine we take a mystery number and we multiply it by 2. We test this new doubled number and we discover that 7 divides it perfectly. That means the atom 7 is absolutely inside this new combination. But look at what we just combined. We just took a 2 atom and we smashed it into our mystery number. Where did the 7 come from? It certainly did not come from the 2. It has no 7s hiding inside of it. Therefore, by pure process of elimination, that 7 atom must have been hiding inside our original mystery number the entire time. It had nowhere else to come from. This is the beauty of numbers that share no common factors. Because 2 and 7 share no common atoms, multiplying our equation by 2 is totally safe. It never fakes a divisibility by 7, and it never destroys 1. It simply transforms the equation into something much easier for us to calculate. And why in the world did we do this? Because 20 is sitting right next door to 21, and 21 is a perfect, beautiful multiple of 7. Because we are always looking for giant chunks to throw away, we can use a clever rewrite. We can split that 20a into 21a minus 1 single a. Let's substitute that back into our scaled-up equation. Our expression is now 21a minus a plus 2b. Look at that brilliant first term. 21a is mathematically guaranteed to be a perfect multiple of 7. It is exactly the giant chunk we have been hunting for. And because we know 7 divides it perfectly, we can cross it completely out. Toss it in the trash, it vanishes from the board. So what is left over? We are left with checking if 7 divides the remainder, which is negative a plus 2b. We are incredibly close. Just like before, it is messy to deal with a negative sign hanging out right at the front. Fortunately, we can invoke our simple mathematical rule. If a number is divisible by 7, its exact opposite is also divisible by 7. We are completely allowed to flip the signs on the entire leftover chunk. By flipping the signs, negative a plus 2b transforms perfectly into positive a minus 2b. And there is the magic completely demystified. We used a exactly as it is. The famous chop off the last digit, double it, and subtract rule is not just some random trick handed down from history. It is the direct mathematical result of taking your number, scaling it up by 2, finding the nearest massive multiple of 7, which is 21a, throwing it in the trash, and flipping the sign on whatever tiny pieces are left over. You just built a mathematical shrink ray completely from scratch. Testing 343. Chop off the 3. Double it to get 6. Subtract from the rest. 34 minus 6 equals 28. Since 28 is a clean, recognizable multiple of 7, we know for a fact that 343 is perfectly divisible by 7. Testing 16,499. Let us keep whittling it down. Round 1. Chop off the 9. Double it to get 18. Subtract from the rest. 1,649 minus 18 equals 1,631. Round 2. Take 1,631. Chop off the 1. Double it to get 2. Subtract from the rest. 163 minus 2 equals 161. Round 3. Take 161. Chop off the 1. Double it to get 2. Subtract from the rest. 16 minus 2 equals 14. Boom! The dust settles on 14, which is a clean multiple of 7. That means our original behemoth is officially in the 7 club. What if our whittling leaves us with a negative number? That is perfectly fine, because negative multiples still count for 7 as well. Let us test the number 119. We chop off the 9, double it to get 18, and subtract it from the remaining part, which is 11. 11 minus 18 gives us negative 7. Since negative 7 is a perfect multiple of 7 on the negative side, 119 is completely divisible by 7. Now, before we move to the rule of 11, if you are enjoying this mathematical journey, make sure to hit that subscribe button so you will not miss any of our upcoming movies. Let's tackle 11. The rule for 11 is remarkably clean. You chop off the unit digit and you subtract it from the remaining digits. That is it. Just a minus b. But why does this work? Let us prove it using the exact same logic we used for 7. We start with our standard structure, 10a plus b. We are looking for a massive chunk that is a perfect multiple of 11. Well, this one is staring right at us. 11a is obviously a multiple of 11. So let us rewrite our 10a as 11a minus a single a. When we plug that back in, our number looks like this, 11a minus a plus b. Just like we did with the rule of 7, we take that guaranteed multiple 11a and throw it right in the trash. It completely vanishes. We are left with checking the tiny remainder, negative a plus b. And once again, we can use our handy sign flipping trick. If 11 perfectly divides a number, it perfectly divides its exact opposite. So we flip the signs on negative a plus b to get positive a minus b. Boom. We just proved the rule. Chop off the last digit, subtract it from the rest. Let us see this in action with 3 examples. Example 1. Let's test 143. Chop off the 3. Subtract it from the front chunk, which is 14. 14 minus 3 is 11. Since 11 is obviously in the 11 club, 143 is perfectly divisible by 11. Example 2. Let's look at 902. Chop off the 2. Subtract it from 90. 90 minus 2 is 88. Since 88 is a clean multiple of 11, 902 is absolutely divisible by 11. Example 3. Let's try a beast, 10,879. Round 1. Chop off the 9, subtract it from 1,087. That gives 1,078. Round 2. Take 1,078, chop off the 8, subtract it from 107. That leaves 99. Since 99 is a beautiful multiple of 11, our original giant number is totally divisible by 11. Now, here's a fun secret. There is actually another incredibly nice rule for 11 that does not require chopping numbers at all. It is very similar to the add them all up rules we use for 3 and 9, but with a fascinating twist. We will explore exactly how that one works in our next movie. So stay tuned. Now, I leave you with a challenge. Based on the logic we have used today, can you find the divisibility rules for 12 and 13? Think about how we built the rule for 6, or how we whittled down numbers for 7. Write your best proofs and answers in the comments below, and I will see you in the next movie.